Illustrated, a mercury manometer is attached to the side of a nearly full water tank. The reading of the mercury column is 15.5 inches mercury gauge. Although air on the water maintains the pressure, the other 10-inch leg of the manometer is full of water. For water, the density is 62.3 pound mass per cubic feet, and for mercury, the density is 846 pound mass per cubic feet. If the location is at the standard gravity and the temperature of both the water and mercury is at 60 degrees Fahrenheit, what is the pressure in psia in the tank at the level where the manometer is attached? If the tank extends 10 feet below this level, what is the pressure at this depth? So, just a suggestion, if you are solving this type of problems in which you are having a hard time visualizing the situation, I do suggest that you draw or redraw the problem, the illustration, so that you'll be able to analyze where the pressures are, and then also in order for you to come up on a way and approach to solve the problem. So that will be the first step that I'm going to do. I'm going to draw the tank. This will be my tank, and redrawing it. Like that, and then just like that. Same. It's a U-shaped manometer. So this is how my tank looks like, and then there are 2 points, the point B and point C at the tank. So this is where point B would be, here, and then point C is 10 feet below point B. This is 10 feet, and then we will have our leveling point, this point. So I'm just gonna shade this one to differentiate our leveling point, and here is full of mercury at the right side, and then this is an open system, so we will have our pressure ATM, or atmospheric pressure, and at this side, at the left leg, this is full of water, and with a height of 10 inches, and the mercury has a height of 15 inches, 15.5 inches inches. Alright, so that is my illustration. And now, in solving manometers, the pressure at the left side is always equal to the pressure at the right side. So that means the pressure, let's identify the pressures that are present at the left side. So the pressure at the left side then be pressure of the water, and then since this is not a full tank, that means there is still pressure present, another type of pressure present at the tank. So I would call this one as pressure tank. So pressure of the tank, that means that the pressure of the left side, pressure tank, plus pressure of water, and then pressure present at the right side would then be pressure of the atmosphere, so pressure ATM, plus the pressure of the mercury, so pressure of mercury. Since the problem is asking for the pressure of the tank, that means we just need to transpose pressure of water. So solving for pressure tank is equivalent to pressure ATM plus pressure mercury minus the pressure of water. Right, so we all know the pressure of ATM is constant, so that would be 14.7 psi, and since we are using English system here, so it is best that we use PSI as our general unit of our pressure. So I already have 14.7 psi for my atmospheric pressure, so my only problem would now then be pressure mercury and pressure water. We all know that hydrostatic pressure is defined as density, gravity, and height, and minus density mercury, density water, gravity, and height of the water and height of mercury. So in order for me to differentiate them, so I'll just put Hg for mercury as a subscript and W for water as a subscript. So the values given are height for water would then be 10 inches, the elevation for mercury is 15.5 inches, and then the density for mercury is also given. The density for mercury is 846 pound per cubic feet, and that is pound mass. And then the density for water, Pw, is equivalent to 62.3 pound mass per cubic feet. And gravity is at standard condition, so the English system value for gravity is 32.174 feet per second squared. And this is a trick, or this is another method. If ever it is stated that the gravity is at standard condition, it is always assumed, or it is always given that pound mass is equivalent to pound force. So there's no need for you to convert pound mass to slug and then multiply it by gravity in order for you to arrive at pound force, because at standard condition pound mass is always equal to pound force, if and only if it is specified that the condition is at standard gravity or standard condition. So if not, then you will have to manually calculate or manually transform or come up or arrive at a value of pound force by combining pound mass with the unit of gravity and then converting pound mass to slug, just like what we did with problem number 3. So in order for us to be efficient and during exams it is time consuming and we are pressured by the time limit, so it is best that you use this kind of shortcut. So let's substitute the values. So 14.7 psi plus our density is given as 846 pound mass per cubic feet. 846 pound mass per cubic feet multiplied by there's no need for us to multiply gravity on this one. We just need to cancel gravity, because as you can see, gravity is only used in order for us to arrive to convert pound mass to pound force. We need gravity, but since it is already in standard condition, so there's no need for us to multiply gravity. We just need to do this shortcut. Pound mass is equivalent to pound force, so I'll just be converting pound mass here into pound force, just like that. And then I'll just directly multiply it to the value of our height of the mercury, which is 15.5 inches, just like that. And then minus the the density of water is 62.3, and then pound mass, since it is in pound mass, since I'll be doing the same, I'll be directly putting pound force here all over cubic feet, and then multiplying it by the height of the water, and the elevation of water is in 10 inches, and just like that. And then in order for us to arrive at a unit of the unit of psi, we need to have the unit of pressure, the unit of force at the numerator, which is in pound force, and the unit of area at the denominator, which is in inches squared. So since both of our denominators of our pressures in for mercury and for water is in cubic feet, we need to convert either one of them. We need to convert cubic feet into cubic inch, so that we'll be able to cancel inch at the numerator, and we will be left with inches squared at the denominator. So what we're going to do is we just need to multiply this, since it's already bracketed, so that means this will be distributed towards these two. So we just need to multiply the conversion. So cubic feet, so we'll put 1 cubic feet at the top, and then converting cubic feet to cubic inch, 1728 cubic inch is equivalent to 1 cubic feet, and then we cancel cubic feet on both of these two, and then we multiply 1728 inches cubed. So the equation will now become 14.7 psi plus 846 times 15.5 pound force times inch, then all over 1728 cubic inch. It's like that, and then we minus 62.3 pound force times 10 inch all over 1728 cubic inch, just like that. Then we cancel inch, so the denominator would then become in cubic and square inch, and then we cancel this one, and then square. So our units will now become pound force per inch squared and pound force per inch squared. So we will have a unit of psi, and then we just need to simplify these values inside our bracket. So 14.7 psi plus, simplifying this one, 846 times 15.5 divided by 1728 equals 7.588. We always during our thermodynamics 1, we always copy the last 4 decimal places, so we will be doing the same. 5885 psi, I'll be putting in psi, minus, simplifying this one, 62.3 times 10 all over 1728 is equivalent to 0.3605 psi. Okay, and now we already have uniform units, so psi, and psi, so we can just simplify directly. So pressure tank is equivalent to 14.7 plus 7.5885 minus 0.3605. So the pressure of the tank at point B is equivalent to 21.93 psi at point B. So this is the pressure of the tank at point B. And now the follow-up question is what is the pressure of the tank if it extends 10 feet below this level? So that would be the pressure of the tank at point C. So in order to have the pressure of the tank at point C, we all know that the pressure of the tank at point B is 21.93, so we just need to add that with the pressure of the water at a height of 10 feet. So pressure tank at point C is equivalent to 21.93 psi plus the pressure of the tank at an elevation of 10 feet. So the formula for pressure is density, gravity, and height, wherein height is equivalent to 10 feet. So we already have a value for density for water since it is given, and the standard gravity. There's no need for us to include gravity in when we are substituting, because as we can see it is in standard condition. We just need to convert, we just need to directly put pound mass or replace pound mass by pound force. 93 psi plus density is given as 62.3 pound. Instead of pound mass, I'm just gonna put pound force here, all over cubic feet, and then I'll skip gravity because that is already included or already part of this pound force. And then I'm going to directly put in 10 feet. 10 feet. And since we need a unit of psi, so we need to convert, we just need to cancel this first, squared, and then we convert feet squared to inches squared. In order to do so, 1 feet squared here at the numerator, and then 144 inches squared at the denominator. So cancel feet squared, cancel feet squared. Our unit would then become pound force per inch squared, which is a unit of psi, which is psi. So pressure tank at point C is equivalent to, so simplifying, 21.93 plus 62.3 times 10 all over 144. So that means the pressure at point C, pressure of the tank at point C is 26.2564 psi. Alright, that's for our problem number 4. Alright, so that's for problem number 4. And now let's proceed to our final problem for chapter 1, problem number 5. So problem number 5, the question is, a 10 feet diameter by 15 feet height vertical tank is receiving water at a density of 62.1 pound mass per cubic feet at the rate of 300 gallons per minute and is discharging through a 6-inch ID line with a constant velocity of 5 feet per second. At a given instant, the tank is half full. Find the water level and the mass change in the tank 15 minutes later. Just like in every situation, in every previous problems that we solved, the first thing that I would do is to draw or illustrate for me to be able to visualize the problem. So I'm just gonna draw the tank. Just like that, and then the diameter is 10 feet, so 10 feet here, and then the height is 15 feet, and then the tank is receiving 62.1, the density is 62.1 pound mass per cubic feet, and then the volume flow rate is 300 gallons per minute, so 300 GPM, and then it is being discharged through an ID pipeline. So let me just draw it like this. It's being discharged, water is being discharged, and then the diameter of this is 6 inches with a constant velocity, and then the velocity is 5 feet per second. And the tank is half full, so at an instant the tank is half full, so like that. Find the water level and the mass change in the tank 15 minutes later. So first things first is we need to list down our given. So our volume flow rate is 300 gallons per minute, and then our density is already given, our velocity, and we need to solve for the volume of the tank also. So since this is a cylindrical tank, the formula for volume is pi r squared times the height. Pi and then our radius is 10 feet. So since the given is in diameters, so 10 feet all over 2 squared, and then times 15 feet. The volume is let me just input here, shift pi times 10 to the power of 2, shift pi times 10 over 2 squared times 15 equals 375 pi, or 1178.097245 cubic feet. But since it is half full, so we are only taking the velocity, the volume initial is half of the value that we have arrived, so it will be divided by 2, 589.0486 cubic feet. So this is our initial volume of the water inside our cylindrical tank. And then we need to convert our volumetric rate, or the volume flow rate, from gallons per minute into cubic feet per second. So in order to do so, we need to have our conversion. So 1 gallon is equivalent to 7.48 cubic feet. 1 cubic feet is equivalent to 7.48 gallons. So let me just input that here. So 1 cubic feet all over 7.48 gallons, and then converting minute to let's just retain minutes. So cancelling gallons, 300. So 300 divided by 7.48 equals 40.107 cubic feet per minute. Okay, and then since we already have our volume flow rate and the density is given, so we can directly solve for our mass flow rate 1. Mass flow rate 1 is given by the formula density times volume flow rate. Our density is 62.1 pound mass per cubic feet, and then our volume flow rate is 40.107 cubic feet per minute. So cancelling the unit of volume, we will be left with pound mass per minute. So our mass flow rate 1 is 62.1 times 40.107 will give us a value of 2490.6447 pound mass per minute. Just like that. So this is our mass flow rate 1, and our goal is to determine the water level and the mass change in the tank 15 minutes later. So since mass change, we need mass 1 and mass 2, so we need to solve first. We have for the mass 1, so we already have it, and then the next thing that we would solve for is mass 2. So mass 2 is would be based on our discharge. Our given and our discharge are the velocity, the diameter, and that's about it. So another formula for solving for mass flow rate, this is the general formula. Mass flow rate is given by density area times velocity. So density is already given, and area we can solve for area using the diameter of 6 inches, and velocity is already given, so we can solve for our mass flow rate 2. So let's first solve for our area. Area is equivalent to, since the diameter is given, so we can use the formula pi d squared all over 4 equals, and d diameter is in inches, so we need to convert this one into feet. So pi times 0.6 inches, that would be 0.5 feet. So 0.5 feet to the power of 2 divided by 4. So value of our area is shift pi times 0.5 to the power of 2 divided by 4 equals 1 over 16 pi, or 0.196 35 cubic feet. Feet squared. That's for our area. And then substituting this one to the formula, mass flow rate 2 is equivalent to the density, 62.1 pound mass per cubic feet, and then our area 0.19635 feet squared, and then our velocity, which is 5 feet per second. Since the unit here of mass flow rate is, the denominator is in minute, so we need to convert seconds to minutes. So 60 seconds all over 1 minute. Now we can solve for our mass flow rate 2. Mass flow rate 2 is, so 62.1 times 0.196 and 35 times 5 times 60 equals, mass flow rate 2 is 3658.0005 pound mass per minute. So cancel this one, cancel. So that's for our mass flow rate 2. Therefore, our change in mass after 15 minutes would then become mass 2 minus mass 1 times the time. Since the time is given as 15 minutes. So change in mass, mass flow rate 2 minus mass flow rate 1 times time, because mass flow rate is given as mass all over time. So in order to come up with the unit of mass, which is either in pound mass or kilogram, we need to multiply mass flow rate by its by time. So that's why we have time here in our formula. So mass flow rate 2 is 3658.0005 minus 2490.6447, and then the unit for both of these values is pound mass per minute, and then multiplying it by 15 minutes, which is our time. So we can cancel the unit of time, so we'll be left with the unit of mass, which is pound mass, which is what we really wanted, because what is asked is the change in mass only, not the change in mass flow rate. So 3658.005 and minus 2490.6447 equals 1167 times 15 equals 17,510. 17,510.337 pound mass. So the change in mass after 15 minutes is 17,510.337 pound mass. And that's for question A. And then for question B is the change in water level after 15 minutes. So since we already have our mass, we can use the change in mass as our clue in order to solve for the change in height. So how will we be able to do that, since we can compare the volume of the change in volume after 15 minutes with the initial volume. In order to do so, we need the change in mass and the density, because as you can see, if you reciprocal density, it will become volume over mass, and then if you multiply it by mass, you will be able to arrive at the unit of volume. So let me show it to you. So let's say volume, change in volume is equivalent to change in mass divided by density. So the unit will now become 17,510.337 pound mass divided by the density, which is 62.1 pound mass per cubic feet. As you can see, this is in the form of division of fraction. So cubic feet will now go to the numerator, and then we can cancel both of these units. So pound mass would be cancelled, and this would be reciprocal. So then the change in volume is equivalent to 17,510.337 divided by 62.1. So the answer would be the change in volume is 281.97 cubic feet. And now, how will we be able to connect this one to our initial volume? So since after 15 minutes, some of the water, since at initial volume it is half of our tank, after 15 minutes, some of the water of inside our tank at half full would be discharged to this ID pipe. That means the initial volume would now be deducted by our change in volume, which is 281.97. So the resulting will now be our volume final. So we need to solve for our volume final. That means volume final is equivalent to volume initial minus change in volume. So solving for volume final, volume initial is 589.0486 cubic feet minus our change in volume, which is 281.97 cubic feet. Therefore, our final volume at 15 minutes, after 15 minutes, is 589.0486 minus our change in volume is 307.0786 cubic feet. And then how will we be able to make use of our volume final as our basis in order to arrive at the value of our height? So let me show it to you. Let me rewrite it. So volume final is equivalent to 307.0786 cubic feet, right? We all know that the formula for volume of a cylindrical tank is equivalent to pi r squared h. So we just need to equate that, and we are going to solve for our height, and this height will now become our height final. So height final is equivalent to volume final divided by pi r squared, because the radius does not change since it is constant, because the tank does not change, only the water inside the tank changes. So the radius here is constant, so whatever radius is given, so that will be the radius that we are going to use. So using this technique, we'll be able to solve for height final. So volume final is 307.0786 cubic feet divided by pi times our diameter is 10 feet, and 10 feet all over 2, because we'll be basing it with our radius to the power of 2. Now we can solve for our height final. So height final is equivalent to 307.0786 cubic feet divided by pi times 10 feet all over 2 to the power of 2. So that means the final elevation, or the final height after 15 minutes, is 3.91 feet. And that's for our problem number 5.